Okay, I think we're back here. Um, I just discovered why my video didn't record last week. Apparently in OBS Studio, when you press the space bar to advance your slides, if you're not actually in the PowerPoint window, you don't advance the slide, you stop it from recording. So anyway, that's why I recorded one lecture twice last week, and this week I plan not to do that again. So the last little while we've been taking a look at tensile stresses and their effect on materials. So stress, uh, the applied force divided by the cross-sectional area, causing strain, the change in length. The change in length has been either elastic, where it springs back, or plastic, where it stays stretched. And ultimately, we keep pulling things through elastic into their plastic range if they're a ductile material, through their plastic range where work hardening occurs, and then the material snaps when it gets to its ultimate tensile stress. So we want to take a look today at some of the reasons why that happens. So we're going to take a look at that at an atomic and crystalline level at what's going on inside some of these materials. We're going to tend to focus on metals and alloys because we're leading into a unit where we're going to talk about hardening and steels. A very, very critical part that's sort of foundational to the industrial technology that we know today. If we couldn't harden steel, we would live in a much, much different world. Okay, let me make sure that I am advancing my slides here properly. There we go. I'm still recording. This is good news. So, just a review. I'm sure everybody knows that our world is made up out of atoms. The atoms were formed, many of them in the Big Bang that we've been able to figure out is the foundation of our universe. And we don't know what happened in the 0th second of the Big Bang, but there's pretty good theories to explain what happened from about 10 to the minus 15th second onwards. And some of the complex atoms that we have were actually formed in the heart of suns and stars that eventually burned out and collapsed and exploded. So really, we are all made of stardust here, and some of that stardust has settled down and formed this planet that we call Earth, and some of those atoms have formed materials that we call metals, and they behave in certain ways. And if we go right back down to the heart of the stardust and inside of it, and start by taking a look at the nucleus of the atom, that's where our story begins on why metals behave and materials behave the way that they do. So just a little bit of refresher from your high school chemistry. The atom is made of a nucleus, which comprises of protons and neutrons, surrounded by a cloud of electrons. And really, what that actually means is that an atom is mostly empty space. And in fact, you and I are mostly empty space. And the catch is that the electrons flying around the atom have strong electronegative charges to them, and negative charges repel each other. So when you go to put your fingers together like that, they don't pass through each other, even though they're mostly empty space, because that empty space is filled up by electronegative fields that repel each other when you go to do that. Critical to the understanding of this is that we've got our elements, the foundational building blocks of matter on Earth, in the universe, I should say, and the atom is defined and named by the number of protons in the atom. Now, the protons have a positive charge, so generally, by and large, there's the same number of electrons that have a negative charge flying around the outside. But in some cases, not quite. We'll take a look at that in just a moment and some of the things that nature does to balance that out. So we also have neutrons sitting in there, and neutrons add to the mass of the atom, but they don't actually affect the electrical interaction between the protons and the electrons because neutrons have no charge. However, changing the number of neutrons can change the isotope of the material. So when you hear people talk about isotopes, you'll probably hear it in the context of a radioactive isotope. That is an atom that has an unusual number of neutrons in it, and it's trying to decay back to a more standard number of neutrons. So the neutrons play an important role in some of the behavior of the material, but usually not in the mechanical structures that we're looking at. We're primarily concerned with protons and electrons. Now, there's a model for how the electron goes together, and it's a simplified model. And like many things that we talk about where electricity and electrons and physics are involved, we try to simplify this down into a way that we can explain what's going on that reflects the behavior that we see, but is not as complex as the fully understood model of what's going on. Because when you start getting into the fully understood model, you'll get people saying, well, there's not really a thing called an electron because it's both a wave and a particle. And it's more of a concept that there's an electron there. It exists kind of as a cloud, and it's a probability field, and it's all kind. No, we're not delving into that. It's fascinating what people have been able to figure out and the theories they've been able to develop and the theories that they've been able to test and just what science has been able to accomplish in understanding the very fundamental aspect of how our world is put together. But for our intents and purposes, we're going to assume that the electron is a single thing and that there's something called an orbital that wants to have a certain number of electrons in it. It's a simplified model, but it's not wrong. Okay, it adequately describes some of the things that are happening when we take a look at the periodic table of elements and how atoms behave with each other. So if we take a look at this chart right here, where's my mouse gone? And so right here, we've got our simplest and probably most common atom in the universe, the hydrogen atom. And the hydrogen atom is one proton surrounded by one electron. And so that's a balanced charge right in there. So in the middle of there, we've got one proton with a positive charge. We've got one electron with a negative charge. And that's nice attraction. They're happy and they're together. So that's why hydrogen is element number one proton. Okay, the position on the periodic table and the numbering of the elements all comes from the number of protons. Helium, okay, right over here, is got two protons, and it also has two electrons, so also a fairly simple structure. Now, what's interesting right here is that the shell that they've filled wants to have two electrons in it. Now, I say wants to have, that again, a bit of a simplification. But if we take a look at this shell as saying, okay, that first layer is only happy when it's got two electrons in it. That's how it works. And the atomic shell model starts filling up the shells from the inside out. So when we go up to the atom that has three protons in it, we come to lithium. And here we've got the inner shell filled and the outer shell, which ultimately is going to want to have 2, 4, 6, 8 electrons flying around it. It's only got one. That is part of the reason why lithium is such a reactive metal. Okay, if you think about lithium batteries, what's our best energy storage medium right now? And we may come up with other things, but right now we use a lithium ion battery because that one electron is not really happy being in that shell because that shell is a long way from being filled. So lithium really wants to get rid of that one electron and have it shared with another element. This is also why lithium is so darn reactive. So if you drop a piece of metallic lithium into water, it's going to start ripping electrons off of the oxygen that's in the water and the hydrogen that's off in the water to start forming happy outside shells. So for instance, If you take a look at lithium right here, it's got one extra electron in its outside shell. Hydrogen is missing one from its outside shell too. So if hydrogen either gives up one electron or gains one electron right here, it's going to have either a completely empty shell, which is like, okay, I can live with that, or it's going to have a completely filled shell, which it's okay, it can live with that as well. Lithium can give up one or gain seven to make its outer shell happy. Okay, now if we drop lithium into water, now water, as you'll know, is H2O. Okay, and the H2O comes into play right here because in oxygen, you'll see we've got two spaces in that outer shell that it would like to fill to bring that up to a complete complement of 8 electrons in the outer shell. Well, hydrogen only has one electron in its outer shell. So if two hydrogen atoms get together with one oxygen atom, they'll say, hey, let's share that electron in the outer shell. You can have it part of the time and I'll have it part of the time. Both of these come out being happy because hydrogen's sitting there going, well, okay, I got rid of that weird electron that was just hanging around the outside, but I get it back every now and then, so the proton's happy. It's all balanced out, but it shares it over here with the oxygen, allowing it to fill up that shell. The total number of protons balances out to the total number of electrons in that arrangement, and the shells are either filled or not filled. So the shells are happy as well because the shells don't like having a weird number of electrons in them. Lithium can come into there, and if you drop it into water, that single electron right there is so reactive, it will come into the H2O and it will say this electron is more reactive than this electron. It will knock the hydrogen out of there. It'll force the hydrogen to form H2, which is hydrogen gas, where two hydrogens join together and one hydrogen shares its electron with the other one. So one of those atoms has two electrons in its outer shell and one has none. Again, two electrons, two protons. The number of electrons and protons balances out, so that's happy. And we have one full shell and one empty shell. It's not quite exactly a perfect explanation, but that's the simplified explanation, is that the number of protons and electrons will always balance out, and you always want the outer shell to either be filled or completely empty. You always want an full outer shell on the outside of your electron. This is also why some of our gases on this side of the periodic table are called noble gases, because they don't really react with anything. So for instance, helium right here doesn't need to react with other atoms because it's got two electrons and a full outer shell to begin with. Neon has 8 electrons and a full outer shell to begin with. Argon down here, these gases you'll see are often used in like argon is used in shielding for your welds because it won't react with the weld and it won't get embedded in the weld because it's a noble gas. In other words, it's perfectly balanced with the correct number of electrons for the number of protons, always a requirement, and its shell is filled when it's properly balanced. So there's a few different examples in here. Table salt that you've got in your house is sodium and chlorine. So sodium has this, where are we here? Na down right there. Again, you can see it's in line with lithium. Sodium's a fairly reactive metal. You drop it in water, it's going to hiss and fizz too. Won't quite explode like lithium does, but it's definitely going to, you don't want to be putting metallic sodium into water because it's got this little one electron sitting on the outer shell, and that's going to start ripping your water apart and creating hydrogen gas. And chlorine down at the other end of the chart, it's missing one from the outside. So the reason that table salt forms, why sodium chloride joins up so nicely, is that these guys can share. The sodium says, oh, hey, I'll give you one extra electron. Now sodium's outer shell is full. It doesn't have that one sitting right there. And chlorine's got the extra one over here. So you've got a balance right in there. So that's a little bit of electrochemistry. The course doesn't delve deeply into that field. It may sound familiar from some of your high school science classes. And I just realized as I look over at my third screen right here that when I was busy moving my mouse around and pointing at the sodium down here, that it disappeared behind the lovely picture of me talking and waving my hands because I don't know. Maybe that makes the video more interesting than just watching a dull slide on PowerPoint. Okay, so this type of bond is something that we call an ionic bond because what we get as a result is we get this sodium ion and a chlorine ion. And the sodium, in the case of sodium joining with chlorine, the sodium gives up an electron. Electrons have a negative charge. So the resulting thing is here we have more protons than we have electrons. So this has a positive charge. The chlorine has one additional electron because it gained that. So it's got a negative charge of one. And these two will join together with each other because this one's got positive electrostatic attraction, and this one's got negative. So these will bond together as a result. And we call the two resulting atoms ions. An ion is just an atom with an unusual number of electrons in the outer shell. Okay, so that's what happens right there. And when you get an ionic bond, those are a very, very, very strong bond. You cannot break those bonds mechanically. Okay, you need to use chemistry to break those bonds. Uh, you can Chemistry can break apart any of the chemical bonds. The nuclear bonds that take place within the nucleus, okay, are where you have to move into atomic physics and nuclear power. And so nuclear chemistry deals with the bonds just inside the nucleus. Chemistry deals with what's going on out here in the outer shells and the orbitals. Now, there's other types of bonds that can form as well. Okay, so one of those types of bonds, that was the ionic bond that we talked about, where you've got the transfer of an electron from one outer shell to another. Here we've got a covalent bond, okay, and it's not quite as massive a shift as the ionic bond. You don't have that complete transfer of an electron. You don't have ions forming. What you've got is the valence electrons being shared back and forth a little bit. So you've got carbon, for instance. This is a methane molecule right here. We talked about our hydrocarbons a little while back. Well, why does one carbon have four hydrogens surrounding it? Well, because what happens here is carbon's got 1, 2, 3, 4 atoms in its valence shell, in its outside shell. Each hydrogen has one. So if they get together, this hydrogen will say, well, I'll share that blue electron with you. Now I feel like I've got two in my outer shell. The carbon will say, great, I'll share that with you, and I'll share another with you, and I'll share another with you, and I'll share another with you. And now I've got a full outer shell myself. Okay, so the results methane, natural gas, and it stores energy really well. And water's also another covalent bond. And again, like the ionic bonds, we're not able to break these mechanically. You have to do it chemically. So, for instance, to break water apart, there's a process called electrolysis where you use electricity to do it. Or you could just drop a piece of lithium or sodium in there and that would start messing around with it. For hydrocarbons, we can break them by heating them up and adding oxygen. And oxygen at high temperatures will come in here and the oxygen will bond with the water. Okay, so one oxygen will bond with these two hydrogens and you'll get a water molecule coming off, usually as steam. One oxygen will bond with these two hydrogens, and you'll get another water molecule coming off as steam. In the process, you'll release some energy. And then finally, you'll get two oxygens come in here, and they'll bond with the carbon, resulting in CO2 if you have complete combustion. And that CO2 will be a new covalently bonded molecule that's going to float up into the atmosphere and cause greenhouse effects. Okay, that's basically combustion and hydrocarbon fuels. Now, carbon's really cool because it's one of the reasons we get excited about carbon fiber and graphene and things like that is because carbon is probably the most covalently bondable material out there because it's got 4 electrons in its outer shell, but it wants to have 8. Make sure I'm holding up the right number of fingers here and not unfortunately making some rude combination of fingers. Okay, so it's got 4, it wants 4 more. So it bonds with itself really nicely. So if carbon joins together, you can end up getting all sorts of different bonding combinations. Now, one of those bonding combinations is for 2 electrons from right here to come over and bond with 2 right here, and then 2 electrons right here to bond right here. You end up getting double bonds across, but then you chain all of that together and you can end up with this long stringy structure. And so here's just some of the many known ways that carbon can come together. So it can bond with 4 other carbons to form a mesh. Okay, it can do a double bond right here along with 2 single bonds, or it can even do a single bond and a triple bond. I haven't seen a C2 molecule that would just be 2 carbons joined together with a quadruple bond. I don't think that happens, but the world of carbon chemistry is advancing every day. So here's some actual atomic structures that we see, and there's some that are getting people quite excited. So for instance, D through F right here, these buckyballs. Now, you have to keep in mind the size that we're talking about right here. Okay, this is atomic structure. Even the highest resolution optical microscopes are probably not able to see this. You'll likely have to shift into a scanning electron microscope to start to see these molecules. But buckyballs have some neat properties because they form this spherical structure. You can actually use them to enclose other atoms and other molecules. And there's been talk and investigation into using these buckyballs to surround toxic molecules and wrap them all up in an inert environment so that we can dispose of certain toxic molecules. The catch is because some of these are quite tiny and because they're very persistent in the environment, they don't break down easily. Uh, there are concerns also that if you let too many structures like that out there, they can float in the air, they can get into your lungs, and as we know from very small pieces of asbestos, having strange materials in your lungs is not good for you in the long time. So there's some concern about being careful and responsible with generating new forms of matter. Nanotubes are another one that are pretty interesting because the idea is that if you can make one long enough, essentially it's going to be stronger than a carbon fiber. And if you can also use them for storing and channeling certain other molecules at a very, very, very tiny micro scale. So there's interest in these structures for electronics and battery design, all sorts of neat stuff. And we've got graphite up here, but we also talked about graphene, which is when you're able to start making a giant sheet of graphite, and it's got all the strength properties of a carbon material. Excuse me for right. Hope that didn't come through too loud on your end. Okay, so we've talked about ionic bonds, where you actually transfer an electron from one atom to another, covalent bonds where they share an electron, and then we've got this type of bond called the metallic bond. That would be our third main type of bond. And it's kind of like the ultimate in covalency. Okay, because in covalent bonding, you've got two atoms agreeing to share electrons. And in metallic bonds, you've got a whole bunch of electrons saying, this is too complex. I'm just going to throw my electrons out there and hope that everything balances out by the end of the day. And by and large, it actually does. You end up with the right number of electrons for the right number of protons, and they just sort of shift around from shell to shell to shell out there, and they don't really belong to any one, but they tend to end up giving you full valent shells. So as a result, this kind of forms a soup of electrons throughout the material. And what's really neat is because they're just sort of soupy and floating around in there, and these electrons are not bound to a specific atom or even to a specific molecule. The electrons are free to flow in there. So if you apply a voltage to a metal, these electrons can flow from one side of it to the other, and this is what makes makes metals good electrical conductors. And sort of depending on the degree and the type and the nature of the metallic bonding that's happening, you get some really, really good metallic conductors and some less good ones. But I can't think of anything metallic that doesn't, in some way or the other, conduct electricity, almost contrary to the idea of the metallic bond. And the other thing that this ends up doing is it ends up slightly polarizing. In other words, putting a small charge onto each of the atoms, because each atom is given off a certain number of electrons and has accepted a certain number of electrons. So on each metallic atom, the nucleus is not perfectly balanced in terms of electrons and protons. So there's a little bit of mismatch in charge right there. And what that causes is the atoms to start forming together into crystals. And it's this crystalline nature of materials, crystalline at a very, very small, low level, that results in a lot of the properties that we see. And we're going to talk about that in just a moment. But before we do, let's review the three bonding types. So we talked about ionic. That's your permanent transfer of electrons. That's the strongest bond. You can't mess with that mechanically. We've got covalent. Okay, so that's kind of like dating. If ionic is marriage, covalent is dating. And our metallic bonds, and you did not know this about metals before today, but I can assure you that your metals are hippies in a free love commune sharing their electrons back and forth with all the other atoms in there. And actually works out really well for the metals. All right, so the metals end up with slightly polarized atoms. By polarized, I mean they have an electrostatic charge to them because they've either given up some electrons or they've accepted some electrons in this extreme covalent bonding that we call metallic bonding. So one end of that molecule or that atom might be slightly positive, the other slightly negative. And what that happens is that ends up making them look to the outer world like Lego bricks. And as you'll know, if you're assembling Lego bricks, you can only stack your Lego bricks and build your Lego pieces in an orderly fashion. Okay, the sockets need to fit onto the plugs. Everything kind of needs to fit together. And that's what happens when metals start to form into metallic crystals. Um, so we can't break those bonds with our forces, but we can cause them to deform, and we can shift things around, and we can break these weaker polar bonds between the atoms and the molecules. And that is where our deformation, our stress strain, our elastic and plastic modulus starts to come into play. So let's just take a look at what we're talking about when we talk about crystals. I've got at least one friend who will tell you that, oh, you've got to get some tourmaline crystal. It absorbs negativity. I told her she had to get some silicon crystals because they form a computer and they transfer knowledge. She missed the joke. Uh, as far as we know from science, there are no magic properties to any crystals. But the thing is, we do know enough properties about them that you don't need to ascribe magical properties and magical thinking to crystals to be amazed by them and appreciate what they are. They are beautiful. They are awesome. Things like this geode shown here took thousands, tens of thousands, hundreds of thousands, maybe millions of years to form and for those crystals to grow and for those atoms to arrange themselves into a structure. But crystals actually also exist every day all around us, whether we're talking about the salt crystal that we sprinkle onto our steak at dinner, or the sugar crystal that you drop into your coffee cup to sweeten things up a little bit. These crystals are around us every day, and in fact, they're inside metals. The fundamental structure of metals is crystalline. Crystals aren't quite as big, they aren't quite as pretty as we've got shown right here, but relative to the actual atoms themselves, those crystals are gigantic. You'll have millions and millions or billions and billions of crystals formed together to create uh, uh, of atoms joined together to create even the smallest crystal. So yeah, so to us humans, a lot of the crystals we see are tiny. Now, Star of India diamond, not so tiny. Okay, but by and large, most of the crystals we need that we're going to be dealing with in metallurgy are ones that we'll need a microscope to see. But even to an atom, anything you can see with an optical microscope is gigantic. Okay. Now, there's a whole bunch of different types of crystal structures, and this is part of the reason where crystals start to get really interesting and why there is a whole field of study known as crystallography. And anyway, it's a really interesting field, very foundationally based on math and placing things in 3D space and being able to describe things in 3D and explain how X-rays interact with them when you bounce X-rays and various forms of light, energy, and radiation through them. It's a really neat field. And the crystallographers have come through and mapped out the lattice structures, the positions of the individual atoms in the different crystals. And although there's 14 common different lattice structures that we could be taking a look at if we took a look at all of our metals. There's two that we really care about. We'll take a look at them more next week, but I'm going to say their names right now so that you get an idea into your head that you're going to be hearing me talk more about BCC, the body-centered cubic structure, and FCC, the face-centered cubic structure, because those two structures are fundamental to steel. And the transition that happens in steel when it goes from body-centered cubic to face-centered cubic when you heat it up, and then back again when you cool it down, that's what makes hardening possible. That and a little bit of carbon. There's some other neat tricks that are happening in there, but fundamentally, it's this transition that happens in iron when it gets glowing red hot that allows us to make it as useful as it is. Okay, so let's take a look at some metallic crystals in here. So metals at a microscopic level are crystalline. And in order to see these crystals, what you have to do is you have to slice the metal, you have to polish the sample, and then you have to take that polished sample etch it with a little bit of acid so that the grain boundaries of the crystals, the edges of the crystal where you've sliced it, remain visible while you eat away the inside of the crystal, or vice versa, depending on what you're looking for. And then you need to illuminate it properly under a microscope, and then you can see what's going on. So in this structure right here, we're taking a look at some copper. And here's the scale we're looking at. This is about 50 micrometers right across here, or 50 microns across there. Keep in mind, so that's 50 times 10 to the minus 6. So a millimeter is 10 to the minus 3. So if you take a millimeter and split it up into 1,000 parts, okay, picture that millimeter and sitting there and subdividing that millimeter into 1,000. Then you'll have 1 micrometer. 50 of those will come together. So this line right here works out to be about 5% of a millimeter. Okay, so that's the size we're looking at. So if I count out 20 of these big long crystals right here, that would be about 1 millimeter long. So 1 millimeter is probably going to be somewhere off on my next screen right here. Okay, so anyway, here we've got some metallic crystals. And before I go on to the next slide, just take a look at these. And is there anything unusual that might strike you about these copper crystals? You'll probably see little dots inside of them. And if you pointed that out and you said, oh, those dots, that's maybe an impurity or something inside the crystal, that is a fabulous observation. We're going to talk about impurities and dislocations a little bit later on. That's something important to note. If you note that they're different sizes, that's good to note too. Now, keep in mind, just like when we talk about wood grain, wood end grain, we're taking a look right here at a two-dimensional view of a three-dimensional structure. So it may be that what we see as a large crystal right in here is just something that we happen to cross section right at the middle of the crystal. And right here, this crystal actually goes down into the material and gets bigger and becomes out to this diameter as well. But here, it's just kind of tucked in, and we're just slicing through the top of the iceberg on the crystal. While here we slice through the main meat of the iceberg, because this is a three-dimensional structure that runs all the way through the metal. But what I was really wondering on here is, did you notice that there tends to be elongation? Okay, these copper crystals didn't start out this way. These copper crystals, you can see if you look in here, they tend to be longer than they are high. Just about every crystal, whether we see just a little end piece of it, whether it's a small crystal or a long crystal right here, they tend to be stretched out this way. And so someone who's familiar with looking at micrographs of metals would look at that and say, oh, this material has been subject to plastic deformation. And when you plastically deform your material, this is actually what you're doing. When you pull on that copper wire and it stretches and it stays stretched, you're taking that material and you're taking it from having nice round crystals, like right here. Well, obviously not round, but sort of equal proportions in high and low, okay, in up and down. Now, they're about the same height this way as they are length that way. And you're taking them and let's just go back one slide, and you're stretching them out so that they become long structures this way. So when you pull on that material, you're actually deforming things at the crystalline level. Now, there's other things we can tell about crystals by taking a look at them under a micrograph. Okay, so here's two different samples with thermal histories. And one thing we know about crystals is that if you give them more time, they will grow larger. because the atoms are able to arrange themselves into that crystal. And so if I start with one atom, the next crystal will join on here, the next crystal will join on here. And just like building a Lego structure, if you've got all day, you can build a giant Lego structure. But if you've only got 5 minutes, you can only build a tiny Lego structure because you've only got so much time to get everything all pieced together before, yeah, I don't know, your kid comes along and knocks it over, which is kind of fun. But anyway, so we can tell from the larger crystals right here that they had more time to form. Now, when do our crystals form? Well, our crystals form when things are heated up because in order for atoms to move around and rearrange themselves, they need to have a hot piece of metal. So I just want you to picture these atoms are all built into a structure. Okay, they're all sitting there in an arrangement. And earlier when we were talking about thermal energy, we talked about the nature of heat being the vibration of atoms. Okay, now if you think about atoms vibrating around at room temperature, they're kind of vibrating like this, maybe, whatever, they're bouncing back and forth. As you start to heat them up, not only do they start to move faster, but they start to move further. Okay, now if you heat them up too much, okay, things are going to form into a liquid. We don't need to go that hot, but they're still a solid, and now they're bouncing around a whole bunch of places like this, and all of a sudden one of them is able to go bloop and jump right over here. And now you've got additional mobility for the atoms to move around inside your atomic structure. I like to make it a little bit of a comparison to going to the orchestra and going to a nightclub. Okay, at low temperatures, you're at the orchestra. Everybody is sitting properly in their seat, waiting for the end of the piece to go and applaud. At the nightclub, okay, everybody's half pissed at the nightclub, but they're now up and they're boogieing around and they're sliding around and they're going around over here and over here. And if you want to get somewhere at the nightclub, you come along and you start swinging your hips and you get out there and you get moving. And depending on the nightclub, you elbow somebody in the face. No, okay, I don't go to those ones. Actually, it's been a long time since I've been to a nightclub whatsoever. In fact, given COVID, it's been a long time since anyone's been to a nightclub, hopefully. So anyway, you want to get up to the bar. Well, you can get to the bar at a nightclub. You just have to get up and move around and get beat around a bit. If in the middle of the performance at the orchestra, you want to go to the bar, the usher's going to have a thing or two to say to you because getting up at the orchestra, and I don't care even if they're playing like Beethoven's Fifth, walking down the aisle, swinging your hips and swinging your elbows like that is not going to be accepted. So low temperature metals are like the orchestra. The atoms are all in their place. They're not moving around a lot. High temperature metals are like the nightclub. They're bouncing around, they're vibrating everywhere, and they can get from one place to another, and they can get organized differently. So temperature plays a big role in what goes on in our metals. Now, the thing is, if you immediately switch from the nightclub to the orchestra. If you immediately go from hot to cool, okay, that's really tough on the atoms because immediately everybody has to settle down. And as you know, if you have left your party at your table at the nightclub and you've been boogieing over to the bar to put in an order for a round of drinks, and all of a sudden you got transported into the orchestra, you have no idea whose lap you might be sitting in at that point. You get these tiny little clusters and these tiny little groupings because nobody had time to get organized. Am I beating this analogy to death? I like beating analogies to death. So if we slowly cool the metal, though, that's like the DJ coming on and saying, okay, everybody, it's last call. Yep, last call coming up in a little bit. I'm going to play a slow song right now. We're going to start quietening things down here. It's time for you to find somebody that, who's sober, who can take you home. Uh, please get out of here. We're getting ready to close. We want to go home. And over the course of about half an hour, you've got a chance to get together, find the people that you came there with, form up into a group, and you can leave in a larger group. Now, or a smaller group if you're lucky. The analogy doesn't work perfectly. Um, as we start to slow things down slowly, you've got time for larger crystals to form as we gradually transition from nightclub to orchestra. So slow cooling allows more time for the materials to rearrange themselves. Okay, now this also has a relation on the material properties. Because these crystals have had time to form, we've got these bigger crystals, and on the side, this one was cooled more rapidly. We've got smaller crystals. And as a result of having smaller crystals, we've got more crystal walls and grain boundaries right here. And these grain boundaries and these little dislocations, you can see they're a little more prominent in right here, are actually getting in the way and blocking deformation. Okay, they're stopping things from being able to move. So this material right here, even though this and this have the exact same alloy content, this material with the smaller crystals likely has a higher yield strength. In other words, it's more difficult to get plastic deformation in the smaller crystals than in the larger crystals right here, because in order to get that plastic deformation, you have to rearrange grain boundaries, and there's a lot more grain boundaries in here that you have to rearrange. Whew. Hey, I think I killed that analogy. But we'll come back and we'll use it again. Don't worry, the nightclub and the orchestra one is a good one when describing what's going on inside metals. All right, so the other thing that can happen is that we can have crystal regrowth. Now, in our first slide, and not the first slide, but in the first micrograph we saw copper that had been stretched and deformed. It had been plastically deformed, and we called that cold working. And the cold working means that as we were deforming it and as we were stretching it, we were actually making the material harder because we were taking some of those original nice soft grain boundaries and we were warping them around and doing nasty things to them. And as we did that, their resistance to deformation continued to increase. Okay. Now, if you had time during your tensile test lab to take one of your stretched pieces of copper, so you took your copper and you pulled on the copper piece and you could feel the plastic deformation happening. And when you were done pulling on that copper, and if you snipped out a piece 1 or 2 inches long and you squeezed it between your fingers, it felt quite a bit different from the original copper. Okay, the original copper would have been softer and more flexible. This stuff would have been harder. It would have been like a little pin poking into your finger. That's because you would have cold worked the copper, making it harder. It wouldn't have been hard like steel hard or anything like that, but it would definitely be harder and have a higher yield strength than the unworked copper. Okay, now that's a good thing sometimes and a bad thing at other times. So sometimes you want to set the copper back to its original point. You want to hit the reset button and say, okay, let's get rid of the cold working that we've done. Now, in order to do that, you heat it up. You take it from the orchestra where nothing can move around, and you take it to the nightclub. Now, as soon as the atoms get heated up to the point where they can vibrate around and move around, they're going to start somewhere around the grain boundaries of the stretched and warped crystals, and the atoms there are going to say, "Hey, do you like this stretch structure? I feel like I'm in the wrong place." And the atom next to it's going to say, "Yeah, like this isn't right. We're kind of deformed here. Um, let's move around a little bit." And so as you heat it up and you give the atoms that freedom to move, they're going to say, we should grow a new crystal right here, and we should grow a crystal that's not warped. So what's going to happen is you're going to start out with something like A. Okay, now this one doesn't have warped crystals in it, but you can picture these being warped. This one just has regular crystals. As you heat it up, okay, things start to form around, and somewhere along the grain boundaries right in here and at intersections, these crystals are going to say, we should form a new crystal. And they'll start growing a new crystal at this point to try and reduce the overall energy caused by the grain boundaries. Now, as they start growing new crystals, you'll end up with a structure that looks something like this in C right here. And now the crystals have started to form together, and now the crystals want to keep growing, and they'll say, well, maybe if we got rid of a couple of these grain boundaries, we'd be even happier. And eventually you're going to keep growing larger and larger and larger crystals, so long as you keep that warmed up to into the crystal growing range. There are some other thermodynamic limits that come into play. It's very difficult to get enough purity and um, that to grow really gigantic large copper crystals in your metal, but certainly relative to the crystals that you originally had, you can probably grow larger crystals with enough time and temperature and heating to make it all happen. The other thing you can do is if you heat up your warped structure, your warped crystals, then, yeah, your warped crystal. Now we're talking Star Trek, right? Scotty, get me some more dilithium crystals. Um, so anyway, you can take your warped crystals by applying heat and heating your copper up to the point where it glows red. You'll regrow some new crystals. You can wait for it to cool down, and then you'll be able to stretch it again because you'll have completely reset all the material properties and undone all the hard working that you've done. So if you pull on that piece of copper and you get it up right up to the point where it's about ready to break, then you heat it up again, you'll be able to pull on it again, stretch it out some more, heat it up again, pull it out and stretch it out some more, and you'll be able to keep pulling thinner and thinner copper wires out of there. So very interesting things that you can do as a result of cold working and crystal regeneration. Now, these grain boundaries really make a difference because although crystals are probably as close to pure and perfect as exists in nature, they're not always perfect. We work very hard with some crystals that we manufacture to make them as perfect as we can get them. In some crystals, like diamonds made out of carbon, that the whole point is to get a perfect crystal. Another place where we really care about crystal purity is in the silicon and germanium crystals that we use for making semiconductors. If those crystals aren't perfect, they don't behave as they are predicted. So that's why when you see people making microchips, they go into a clean room and there's no dust or anything weird. They filter it down to the tiniest level and they grow these crystals very carefully, and then they test them and they throw them out if there's impurities or that in them because they need really, really pure silicon and germanium crystals to manufacture semiconductor devices. But on their own, the crystals that we're looking at in our metals are not perfect. They contain these things called dislocations. In other words, just random deformations that exist in there just as a result of thermodynamics. Because we didn't do everything perfectly when we were growing that crystal. We just heated it up to some random temperature where it was glowing. We didn't achieve the optimal conditions for crystal growth. So every now and then you'll have a dislocation stuck into the crystal, or of course you come to the edge of a specific crystal and you'll come to a grain boundary there. So the grain boundary is the edge defining the crystal, kind of like a cell wall defines the edge of a plant cell. And just like that cell wall at the edge of the plant cell is where a lot of the strength of the plant comes from, the grain boundaries do have an impact on the strength of our material as well. So inside the crystal, we've got these dislocations, and they can actually slide past each other, and they allow for some deformation within the crystal, and they'll keep sliding until they either bump into something we call an inclusion or until they bump into a grain boundary. Okay, here I use the word precipitate. Precipitate is another one of the types of inclusion. So those dots, okay, will form in there, and this dislocation will slip along there until it bumps into a dot or until it bumps into a grain boundary, and then it'll get locked up. So when we're hardening materials and we're making alloys, particularly our non-ferrous alloys, those dots, the precipitates that form inside the crystals, are a real key to controlling how hard and how strong that material is going to be. Whew, there's a lot going on. So, a few things to take away. Metals are formed of many small crystals. Size of those crystals depends on the thermal history of the metal. So if you heat it up high enough and cool it down slow enough, you'll get larger crystals. You can deform a crystal by applying stress to it. You can't destroy the bonds. Those bonds can only be destroyed chemically, but mechanically you can shift things around and change them up because dislocations, random or disorientation within the crystalline structure can pass through a crystal, allowing it to deform, so long as those dislocations don't get trapped or stopped by grain boundaries or precipitates. So when your dislocations can no longer slide through the crystal, when all of them have slid to the point where they're trapped by precipitates or grain boundaries, the metal can no longer yield. It can no longer get longer or physically respond to the applied stress. It's been fully work hardened. At this point, if you pull any harder, the only thing left for the material to do is to break. And so everything will have slid past each other, and the atoms will have slid past here, and then they'll come together and they'll lock up on a grain boundary or they'll lock up on a precipitate. They'll be trapped, and the crystal will be trying to deform, and everything is about as deformed as it's going to get. And when you pull that little bit extra, you'll now go from plastic into ultimate tensile stress, and it will fall apart. So that explains a little bit what's happening. When you're in the elastic deformation range, okay, what you're doing is you're stretching the bonds between the atoms inside the crystal, but you're not quite stretching hard enough to cause one atom to jump past the next one. You're not allowing those, putting enough stress in to cause the dislocations to permanently start moving. When you hit the yield stress, your transition point between elastic, where everything springs back, where you just sort of stretch the bonds, to plastic deformation, you start to have atomic layers slide past one another. If you can think of a whole bunch of balls in a row, you pull them up, pull them up, pull them up, they'll keep springing back. That's your elastic deformation. You pull a bit harder, and boom, they all move one ball to the left. Plastic deformation right there. They'll keep going badoop, badoop, badoop along there as the dislocations slide past each other. Those dislocations are now going to lock up onto either a precipitate or a grain boundary, an inclusion inside the material, an impurity or an alloy element, but we'll call it an impurity, or the grain boundary itself at the edge of the crystal. They'll lock up on there, and there's millions and millions of dislocations. So your first one might lock up and you'll have a little bit of work hardening, and then you'll pull, and then your 10,000th one might lock up and you'll have a little bit more work hardening, and then finally all of your dislocations, all of your slip planes will have slide past. You've done all the slipping that you can do, and then finally, ding, you'll pull that little bit harder, and your work hardened piece of material is going to break. Now, because the plastic deformation is associated with this slipping of crystals and the deformation of the individual crystals, and because crystals will regrow when you heat them up, you can take a piece of copper that you have stretched and pulled and stiffened and work hardened, and you can hit it with a little bit of flame. You can heat it up, and within that copper, new crystals will start to grow. And those new crystals, as they start to grow, will reset the properties of the material and will undo the damage that you caused by your work hardening. Okay, so it starts at the most stressed grain boundaries where the atoms are just like, oh, we're all crammed together because of what that human did. And they don't actually say that, but I like to personify inanimate objects. And so the new crystals will have new dislocations inside them, and you'll be able to restart the process all over again. They call this process annealing. Some people are also familiar with the term normalizing, and basically it's a process of crystal regrowth. And doing it for a long period of time or at a higher temperature, you'll grow bigger crystals and you'll have fewer grain boundaries, and as a result, a softer metal capable of greater strain to failure, more plastic deformation before it breaks. Our elastic deformation, as I think we touched on earlier, caused by stretching of the electric and polar bonds. Okay, now keep in mind, uh, these electric bonds are like super high strength magnets holding two things together. And as you know, if you've got two magnets, you can pull them apart a little bit and then they'll still pull back together. But if you pull them apart too far, then you lose that attraction between the magnets, and they'll blip past each other. Okay, so when you in an elastic deformation, that's everything's still kind of stretchy because it'll all spring back. Your plastic deformation, you apply a sufficient force that the dislocations slide past each other. You've broken you haven't broken the bond, you've just caused everything to slide one bond to the left. Okay, permanently changes the shape of the crystal. If you want the crystal to go back to its original shape, well, you could try compressing it, but that's just going to result in all sorts of weirdness. You'd never get it quite back into the same original shape. In fact, you'd end up generating a whole bunch of new work hardening stresses on there, and eventually that would lead to a fatigue failure where all the different dislocations start to build up on top of each other. And anyway, as you do your plastic deformation, all of these planes slip past each other, starting to lock things up, causing work hardening. And finally, you reach the point of failure. And this is where the dislocations can no longer move at all. And you apply more stress, and they finally say, that's it. I'm done. I'm out of here. And, you know, just looking at the time, we hit the 1 hour mark on this lecture. You're probably feeling the same way. And that's perfectly fine, because if I take a look at our next slide, you'll see that it is the last slide of the presentation. And well, it's going to make all of this sound interesting. No, it should be interesting. It's going to make it sound simple, because we are going to take a look at the iron-carbon equilibrium diagram. And it's magical. It explains so much about what goes on in the heating and cooling of metals. It is If you watch, I'm trying to remember, the Forged in Fire or whatever they call it on TV, where all the bladesmiths go against each other. They're given a hunk of scrap metal and they've got to recreate this blade from the 15th century and blah, 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 this and blah, and, they touch on, I'm going to heat it up and I'm cool it. I'll quench it this way and I'll do this and I'll do that to it. And the whole time they're doing it from an entertainment point of view, and they're more interested in showing you the fire and swinging a knife through something and voting someone off the island or whatever the hell they do at the end of the show. They could make that so much more an educational and interesting show that, okay, nobody would watch. They understand this, but I would, if they just get into the iron carbon equilibrium diagram and show where they're taking it on the chart and how they're coming back, and start talking about time temperature transformation diagrams. And right, okay, it gets me a little bit excited. I think some of this stuff is pretty cool. It explains how a lot of our world works, and I hope I'm sharing some of that enthusiasm and at least a little bit of the understanding with you through these lectures. We'll talk more about it in class and next week. Until then, keep smiling.